We're going to continue to look at exponential functions today. And yesterday we just kind of looked at what an exponential function is, what the graph looks like. Today we're going to look at some actual applications, similar to this problem where we had our exponential function of base e. But first let's kind of look at a problem. The cost of a toy is $10. If the cost increases by 2% a year, what's the value of the toy next year? Well, to do that, we want to figure out what is 10%, or excuse me, $10 with 2%, and we can do that on the calculator, 10 times 2%. And we get 2. So next year we take our $10 plus our 20 cents and we get 10.20. Now if I wrote these at the same time, this is really 10 plus, now instead of 0.2, let's write it like this, 10 plus 0.02. So if I factor out the 10, really, if I wanted the amount to increase by 2% per year, I could just multiply by 1.02 and get my 10.20. Now let's look at another example. Now I want to figure out what's the cost of the toy in 3 years. Well, my first year, excuse me, was 10.20. So if I want to figure out my second year, I can take 10.20 times 1.02. So that's 10.20 times 1.02. So I get 10.404. Now if I want to find the third year, I can take my 10.404 times 1.02 to figure out what is my total for the third year. And I get 10, and we'll round it off and say 61. 10, 61. Now, let's say I would go all the way back to the beginning. And I want to go from $10 right now, increases 2% a year, and I want to try to go right to 3. I don't want to have to figure out what is it after 1, what is it after 2. But if you think about it, all I did each year was I multiplied it by 1.02. So I just took 10 times 1.01, 1 times, 2 times, 3 times, which is the same as just cubed. So I could have done 10 times 1.02 cubed and got the same answer. So what this allows us to do is if I want to find my total into the future, I just have to raise it to that exponent for the number of years. Now, similar problem, but a little different. Let's say it decreases. Same thing, 10 times 2% is 0.2, 10 minus 0.2 is 980. But that's really like 10 minus 0.02. Factor out the 10. 10 minus 0.2 is the same as 10 minus or times 0.98. So if I add or increase by a percentage, it's just 1 plus that rate. If I am decreasing by a percentage, it's 1 minus that rate. And if I want to know what's the total in 3 years, if it decreases by 2% a year, that's just 10, 1 minus 0.02, which is 0.98, cubed. So instead of having to figure it out every year and figure out year 2 to figure out year 3, I can just jump right to year 3 and get 9.41. Now, the formula we're going to use for this is this formula right here. AT equals A naught 1 plus R to the T. Now, A naught, that is our initial, let's try that again, let's see if we can write initial better. This is our initial amount. And it's just not letting me dot my I's here. Let's try it one more time. This is my initial amount. That A naught. This R is my rate per year. And this is my time in years. One important thing is these units have to be the same. My rate and my time. If my time is in months, then my rate has to be in months. Okay? So let's look at an example. You invest $1,000 for 1 year at 10%. How much do you have after 1 year? So my initial amount is 1,000. My rate for 1 year is 10%. So it's 0.1. For 1 year, my T is 1, and I get my answer in my calculator. 1,000, 1 plus 0.1 raised to the 1, and I get 1,100. So, take another example using our same formula. You invest $1,000 for 1 year at 10%. How much do you have after 1 year if the interest is compounded monthly, or every 6 months, excuse me? So now what they do is they calculate your interest in 6 months. So we have 6 months the first time, and then they do it again for the next 6 months. So for the first 6 months, my rate is not 10%. For 6 months, my rate is 5% for 6 months. And then it's 5% for the next 6. So I have $1,000, 1 plus 0.05 for 6 months. And then I have 1 for my 6 months. That's how my rate in units are the same. So if I do that, I have 1,000, 1 plus 0.05, and I get 1050. Which is what you expect, right? If you look up top, after a year, I have 1,100, so 1050 plus 1050, right? Not quite. Let's do the next 6 months. Now, after the next 6 months, I don't have 1,000. I have 1,050. My rate is still for 6 months, 6 months. And so now what do I get? Now I have 1050 times 1 plus 0.05. And I get 1102. Why do I get more in this example than I did in the top example? Up here I only got 1,100. Now I got $1,102.50. Now it's not a lot, but let's say instead of 1,000 it's 1,000,000 and move the decimal point over, it'd be a few more dollars. So by compounding it every 6 months over compounding it just once a year, I got more. So if every 6 months is good, what if I did it every month? So here was our last problem we did, and we had 1,050, right? Now, we're going to use a different formula now. If we're compounding it n times a year, we now have this formula. And compared to the formula over here, you can see we have added in, from this formula over here to this formula over here, we've added in this n. If it's n times a year, we'll use this formula. If it's once a year, we do it over here. So over here, we do 1,000. The rate's 10% per year. Maybe. 10% a year, which is 0.1. But we compound it every 6 months. So how many 6 months are there in a year? Well, that's twice. Then we have 2 times 1 year. And if we put that in our calculator, we will get this answer right there. So we have 1,000, 1 plus 0.1 divided by 2 raised to the 2. We get the same answer. Now what happens if we don't do it every 6 months? Let's do it every month. So if I got more money after 6 months, shouldn't I get more money every month? Every month would be 12. Let's see what we get. So we have 1,000. 1 plus 0.1 divided by 12, 12 months in a year, raised to the 12, and I made a little bit more. It's 7, 1. So, not a lot more, but $2. So if I made more doing it every month, let's do it every day. Let's do it every hour. Let's do it every minute. What happens? Well, we get this. If we do it daily, 360 or 365, we all know that daily is 365, and I'll explain later why 360 is in there. But notice, if we go daily, we get $1,105.16, we round up. If we go to hourly, that's 8,760 times per year. You didn't know how many hours there were in a year. We get 2 more cents. If we go to every half hour, now there's almost 18,000 half hours in a year. We gain thousandths of a cent. If we go every 15 minutes, there's about 35,000 15 minutes in a year. We get even less. And if we just go to infinity, we just do it nonstop every second all year. We go to $1,105.170918. So you can see, this is our N, right? As our N goes up, we don't add much. We eventually kind of level off. We stop. And this is, if you remember yesterday, this formula right up here, 1 plus R over N to the N. I got rid of the T, got rid of the initial amount. And as N gets bigger and bigger and bigger, this gets closer and closer to E. 2.718 ... So when we talked about the natural exponential function, and I just kind of said, well, you're not really go where it comes from. This is where it comes from. It comes from this fact: as we compound it more and more, our N gets bigger, we get more and more money. Euler discovered this. He was looking at compound interest. He was a German mathematician, and he looked at compound interest. And he realized the more I compound it, the more money I get. So instead of doing it once a year, or twice a year, or monthly, or daily, or hourly, I'm going to do it all the time. And he looked at it and said, well, what happens as this number gets bigger? What's it get close to? And if you just look at this, and you look in your notes from yesterday, we get our E. That is where E comes from. It comes from this financial, looking at compound interest and money in a bank. What that leads us to is what's called continuously compounded interest, where we have this formula where we change this 1 plus R to the N to the NT. And we just change that as N basically equals infinity. This becomes E to the RT. And that comes back to this over here. Actually, this was a 1 here. This comes back to this idea of an E over here. So now if we want to say it's compounded continuously, our N is at 12 for monthly or 365 or 360 daily. We can just go to compounded continuously. So, let's look at another example. A bank has a savings account that can double your money in 12 years. Is that good? Find the yearly rate. Well, we're going to go back with a simpler formula to make this a little bit easier. And we would figure out, what do we want to start with? But the bank's going to double our money in 12 years. So let's make this easy math as possible. I'm going to start with $1. So 1 times 1 plus R. This is double your money in 12 years. So that's 12. What's that going to equal? If it doubles my money, if I start with 1, I got to end up with 2. So my equation is 1 plus R to the 12th equals 2. Now I got to solve that. I'm going to take the 12th root of both sides. So 1 plus R is the 12th root of 2. Subtract 1 from both sides, and we end up with R is the 12th root of 2 minus 1. So let's see what that is. This is 2, and the way I'm going to do the 12th root is I'm going to do a rational 2 to the 1/12. I'm going to subtract 1, and I get 595, or in terms of my rate, that's 5.95%. So, if a bank doubles my money in 12 years, my interest rate is around 6, which is actually an outstanding rate. You're not going to find a bank anywhere around here that gives you 6%. So it takes a long time to double your money in a bank where your interest rate's very low, and usually now they're under 2%. Okay? There's another way to kind of use that formula. We're going to skip that. Now, we're going to stop there. That's the first part of this video, and then we will have a homework that kind of goes with this video, then we'll go on to the next part.